Okay, so just a couple of slides to wrap up, and as I alluded to earlier, really focusing on the integration of the seismic and the MT data and some of the isotopic data that Dom was just talking about. So to start, I just as I was finishing up earlier, I was talking about control and influence over those cover sequences, and so I thought I would just come back to quickly highlight the difference between the Leichhardt superbasin, which is in bright green here. It is thicker and more continuous based on the seismic data. We have constraints on, its near surface position. So on the M6 line, we're at the edge of outcrop. And based on the continuity of seismic reflections, it seems to be fairly thick and continuous. And similarly on CF3, and we know then it's at surface, and we can map it on some of the other seismic lines going to the east. It because I always thought of the Leichhardt River fault trough as the big main depot center of the Leichhardt superbasin, when in fact what we see in the west, and even going right up to the M3 seismic line, is that package is potentially less voluminous. It's still got a substantial thickness. It's still, up 3 seconds thickness, so up to 9 kilometers, but it's not as extensive as it is in the east. And so thinking about that, and I will start trying to do my restorations further back in time, I would argue that the Gija suture or structure is probably a likely feature to have been controlling the deposition of those cover sequences back at Leichhardt superbasin time. And certainly we can see here nicely on these sections how the Kurri-Dala Soldiers Cap group is localized over that structure as well. Now, so looking at, I thought I had another image there. Anyway, okay. So looking at M6 and CF3. So this is the MT data, and this might be a slightly different version than Janelle just showed. The upper images from Jiang et al., the 2019 paper. And you can see those features, which on M6 look a little bit plainer until you put the main boundaries from the geology on top. I've filled in, the granites here a bit. But you can see those main features, and you can start to see the relationship with those interpreted basement terrains and overlying cover sequences. So so not only, as I highlighted going through the seismic, the seismic data shows remarkably similar geometry between these two lines, and they're 100 kilometers apart. The MT data, as Janelle flagged, is remarkably similar. So we see features related to moderately dipping structures, because we often think about, if a fluid or magma wants to get to the surface, then it's going to take the most direct route. And that's often going to be the steeper structures. But we do appear to see some clear associations with the moderately dipping structures. So with the Gija structure, and then with these east dipping structures within the central Isa terrain, and then in the overlying cover sequences. So both on CF3 and on M6. So that's really interesting and something to think about. Now, just while I'm looking at this one, I will say, so Fatima's question about the resistive feature, it does seem to be dominantly in Pitta Pitta, and it goes up into the cover sequences. Now that, in this case here, we're centered on the Kalkadoon Leichhardt belt, volcanics and granites, and actually this whole extent comes down a bit deeper on M6. So it goes up into there. So I would say first pass, it's localized and focused around that felsic granite volcanic package and in the Pitta Pitta, and the central Isa is less clear. Central Isa here clearly has some conductive anomalies within it. Oh, this is the one where I did it. So here, just showing the MT data on its own, and then the with the seismic interpretation over top. So just to um, go back and forth once or twice, so you see the comparison of those main anomalies, and then with the structures on top. So the geology, the structure, and the alteration zones that we're seeing related to these being evidenced by these conductive anomalies are really quite consistent through this southern Mount Isa area. Now, just zooming in on the M6 line, and I've highlighted, and this is about discussion really. So as I flagged, we see the association between the moderately dipping structures and the conductive anomalies here, and it's interesting to consider their role relative to some of the steep structures. So Pilgrim Fault, by definition, I think is an upper crustal feature, but there is some disruption of this boundary, and there clearly are steep structures that continue. There's some steep structures here that I think go fairly deep, whether they go all the way through the crust or not. And again, Cloncurry Fault I see as a mainly upper crustal structure, but there certainly are features that suggest there is some reactivation or continuity into the lower crust. So this is part of what I wanted to throw out, I guess, for discussion in the follow-up. So the moderately dipping structures I see as being active during that main shortening event, whether we want to refer to it as D2 or not. During that main shortening event, they are clearly active. Um, are the anomalies related to fluid, to magmas coming up through the crust? Certainly, this numal crust is going to be the source area for the Williams, Naraku, and Marramungi suites. So did they ascend partly through gently dipping structures, or should we really be looking harder for the steeper structures? I think so. There's that early stage of deformation where we're really focused on using those moderately dipping structures. But then as you go to the later stages, and certainly some of the mineralization stages, in the typical copper gold ages, D3, D4, D5, then how deep do those steep structures link, and where are fluids coming from at that time? So just some things to think about and argue about as we come back in. And just to summarize, because I highlighted earlier the difference in the dip of the Gidja structure and in the south versus the north, and we can see how the MT anomalies change as well. So where we're in the north here, where we have the more competent numal west block, you can see that's the area where we have the stronger conductivity anomaly along the suture itself and into the overlying material, both to the west and to the east. So it's interesting to think about the source of that anomaly and how it may differ to this area down here, and potentially in relation to the changes in the blocks. So perhaps up here we have caught up serpentinized mantle or slivers of oceanic crust that have then been altered, and we have conductivity anomalies related to those effects. But again, as Janelle said, there's a lot of work to do to test out the options and think about which what source is going to produce the anomalies we see. So I will leave it there